There's something wrong with your tape measure. Look at the metal hook on the end. Grab it with your fingers and wiggle it. It moves. It actually slides back and forth, maybe a 1/16 of an inch, maybe a little more. If you bought a cheap one, your first instinct is to assume it got knocked loose in your toolbox. But if you pick up a brand new, top-of-the-line Stanley or Lufkin still in the box, it wiggles too. Every single one of them does. It looks like a mistake, but here's the surprising truth. That wobble is the whole point. Today, we're uncovering the mystery of the sliding hook, how a tiny mechanical gap works as a precision calibration system, and why the tool you've been using your whole life is far smarter than it looks. To understand that tape measure hook, we first have to look at what happened before it. Early measuring tapes were essentially just fabric or thin steel ribbons with a fixed end, a hard, rigid stop. Simple enough, but carpenters and machinists kept running into a maddening problem. Measurements taken from the outside of an object didn't match measurements taken from the inside. You'd measure a door frame opening from jamb to jamb, then try to cut a board to fit and it would be off. Not by much, but in woodworking, in metalworking, in any trade where fit actually matters, not by much is the same as wrong. The culprit was the hook's own physical thickness. That metal end has to have some material to it, and that material was throwing every outside measurement off by exactly its own width. So what did people do? They started measuring from the 1-inch mark and subtracting. Or they'd add an assumed offset. Clunky workarounds that introduced their own new errors. There had to be a better way. And sometime in the early 20th century, a toolmaker figured it out so elegantly that nobody has changed the basic design since. What most people assume when they finally notice the sliding hook is that it's just a loose rivet, a quality control oversight that somehow passed inspection. And even people who know it moves often think, oh, it compresses when you push it against something. Which is partially true, but if that's true, why don't we just use a thicker, stiffer hook and solve the problem permanently? Here's what's actually happening inside that little metal end. The hook is riveted to the tape blade, but deliberately, precisely, loose. The amount of play it has is not random. It is machined to equal the exact thickness of the hook itself. Think of it like a self-correcting scale that zeroes itself out depending on how you use it. When you hook the tape over the outside edge of a board, the hook slides out by its own thickness. So you're measuring from the true face of the material, not from the far side of the hook. When you push the tape against an inside surface, say, measuring the interior width of a cabinet, the hook slides in by that same amount, compressing flush. So again, you're measuring from the true surface. In other words, the hook is always finding true zero, regardless of which way you're measuring. The blade never changes. The markings are always the same. Only the hook moves. And that movement is so precisely tolerance that a well-made tape is accurate to within a few thousandths of an inch. But here's the weirdest part. This means your tape measure is simultaneously calibrated for two completely different physical configurations, with no switches, no buttons, and no user input whatsoever. You can hand this tool to someone who has never heard this explanation, and they will get accurate measurements inside and outside without ever knowing why. That's not sloppiness. That's engineering hiding in plain sight. So why is the hook designed this way and not as, say, a removable cap or a manually adjustable zero set? This is where physics and competitive economics collide, and the economics are the more interesting force. Once major manufacturers standardized the sliding hook solution in the mid-20th century, every other manufacturer had to match it. If your tape measured differently from a competitor's, a carpenter couldn't mix them on a job site. That's commercially catastrophic. The sliding hook became the only acceptable answer, not just because it was clever, but because the moment it dominated the market, deviation became impossible. One elegant solution, adopted widely enough, stops being a choice and becomes the law. And this is where it gets interesting, because that same dynamic plays out in dozens of other tools you own, all quietly standardized by the same invisible competitive pressure. But here is where it gets complicated. A worn tape measure, one that's been dropped, yanked, and abused for a few years, can have a hook that's shifted. The rivets loosen further than intended. The play becomes greater than the hook's own thickness. And now your self-correcting system is quietly lying to you by a small but consistent margin. The tool still looks fine, the numbers are still crisp. But every measurement you take is slightly off in a way you'd never catch without a calibrated reference. Think about that cabinet door in your kitchen that never quite closes flush, or the tile row in a bathroom that drifts just enough to be visible at the far wall. The blame usually falls on the installer. Sometimes it belongs to a tape measure that wore out quietly years ago and never announced it. Next time you pick up a tape measure and feel that hook wiggle between your fingers, don't see a loose fitting on a cheap tool. See a passive calibration instrument, one that's been solving a geometry problem on your behalf every single time you've used it, without batteries, without adjustment, and without you ever needing to understand it. The imperfection was the mechanism all along. The hidden logic in tools goes deep. The tape measure is just the entry point. And once you start looking for this kind of compressed ingenuity in everyday objects, you find it everywhere. If you like understanding how the world really works, hit like and subscribe for more. Now go wiggle that hook. You'll never look at it the same way.